So now I'm going to introduce someone who, again, as most of our keynote speakers, needs little introduction, but it really cannot be overstated how much Herb does for C++. Not just all of his work on the standards committee, all the wonderful papers he writes, the contributions he gives to various other projects, but also all the work he does for this conference, all the work he does for this community, making it a better place to be. So please join me in giving a very warm welcome to Herb Sutter.
Thanks, John. Thank you. Well, thank you for that warm welcome. Thank you for that introduction. And thank you all for being here this week. And here we are, Friday, just about evening. And I hope you enjoyed the week. I certainly enjoyed so many of the talks and the panels, the breadth and differences in people that we could enjoy no matter what sector we're in, what way we use C++, where we live in the world or anything else, that we have a lot in common here. So if you enjoyed some talk sometime this week, possibly multiple in the same time slot where you're going to get the next one on YouTube, please join me in thanking all the speakers, all the volunteers, and everyone who made this conference possible. It's such a delight. So thank you very much for that. Let's talk for a moment about a topic that is very general, just as a lead-in to the topics specifically of exception handling and of runtime type information, which are the two main things that we'll talk about 70% and 30% in about that order. But first, it's useful to have some perspective, because it's very easy to solve a point problem. I see a problem, I'm going to attack that. But no problem exists in a vacuum. And there are usually many and often principled reasons to address a problem. And so I want to set the stage for why I think these are important, because there are many other problems we could be trying to solve. And as you know, I'm working on several different proposals, but why these particular ones? So first of all, Andre, how many of you enjoyed Andre's keynote? I cannot promise to be as entertaining as Andre is. I don't know if that's humanly possible for anyone else, but he is such a troll sometimes. So he trolled you with some assembler, said you have 15 minutes to recognize this common algorithm, and then after about 5 seconds he said, or you have 15 seconds, then after about 5 seconds he said, no, it's just some random assembler just trying to get your attention. This is not that. This is a real piece of assembler, and you will get 15 seconds, and I'm curious to see what you think of it. Please raise your hand when you think you recognize what this is doing. Did I miss any hands? I see a hand. Just yell out what you think it's doing, a couple of words. Say again? Is space? No, but that's a valiant effort. Anyone else want to shout out one more? Dynamic, I think I heard, did I hear dynamic cast? What, in 5 instructions? Are you kidding me? Well, kind of, sorta. If I take out the redacted parts, you'll see that the first 2 loads are about vtable pointers. And then we do a range check to do a cast. This is in 5 instructions, ignoring you can also do a null check, which is 2 more instructions than the top, but that can often be elided. This is a 5 instruction dynamic cast that cannot do the general dynamic cast, but that can do down casts, not cross, but down only, and not across a virtual inheritance link. Turns out if that's all you need, we can do that way more efficiently than today. We'll come back to this example at the end of the talk. So to set the stage, this is the context I was talking about. last year, I showed this slide about what is C++. It was actually several slides, and this was sort of the culmination. And working from the bottom up, it was about saying what things are not core to C++, like any particular syntax. We add in syntax all the time. Tedium, lack of good defaults, just ugliness is not core to C++. It's just something we put up with sometimes, and we try to fix it. And also the middle part, backward source compatibility is not really core to C++, but it's very important to adoption, adoptability, migrating code bases forward. But it's really the top part, and especially the first bullet I want to focus in on for today. The zero overhead principle, that I can write zero overhead abstractions. It is true there are no zero cost abstractions, because zero overhead does not mean zero cost. The people often make this mistake, so let me be very clear what zero overhead means. Two things, they're both on the slide. You don't pay for it if you don't use it, and if you do use it, you can't do better by hand, and we know you're C and C++ programmers, so you're gonna try. But if you do use it, you can't do better by hand. What those two things add up to is there is no valid technical reason not to use the feature. And as we evolve C++, one of the things that we're observing happening before our eyes is largely we are moving to be a more static language. We still have virtual functions and we love them, but instead of the 90s when everything was about OO, we are doing more and more templates since the 90s, and it's only been ramping up from there. We are doing contracts, for example, soon. They almost made C++ 20, hopefully C++ 23, which yes, can be about runtime checking, but they're also about static checking, enabling static analysis. And so this talk is talking about how static can help us, because very often when we find we have a performance problem, in the language especially, often the root is the word dynamic. And if we can make dynamic be static, that is often a good solution path to fixing the problem that we're facing. As we evolve C++ historically, and you can quibble about sort of the sizes of these, I'm gonna give sort of a rough priority. We have been very good at adding things. We just are shipping a C++ 20 standard next year that has many major features. It's the biggest feature release since C++ 11. So we're very good at adding features. Sometimes we fix things. And by this, I don't mean sometimes we fix things by adding features, but in this category, I'm specifically saying we take an existing feature and say we add an incremental knob on it or something, like for instance, enabling this capture and move capture in lambdas. We already had lambdas, but certain cases were hard to use, so we had to go and fix it. So we do some of that, but perhaps not as much as we're good at adding new shiny things. And rarely, in part because of backward compatibility, rarely do we actually simplify something in place. Now, often we simplify by going to the top thing, by adding a new feature that subsumes the bottom one, but that means we now have a language that has both of them. So we have using aliases are much more general than typedefs, but typedefs are still there, code still compiles. So what can we do to simplify? We haven't maybe done as much there, and in part, in fairness, we couldn't because of backward compatibility. So I have a modest proposal. What if, in future C++ evolution, we reversed the amount of effort we put into those three things? Is that something you would be interested in seeing as C++ evolves in the next 5 or 10 years? Well, that's heartening. Now, easier said than done. But, first we have to have an aspirational goal. And notice there are some arrows on the screen because sometimes we do need to add things. So some of you, I'm sure, are thinking, but Herb, you're talking about metaclasses, which is now a thin layer over reflection and generation. You want to add reflection to the language. Yeah, that's a big thing. But it greatly simplifies the code we write. That's why I want to add it. So when we add things or when we fix things, it should be with a view especially to having a simplification target. And so I'm going to present the things, especially with exception handling, that I'm going to present in this context with a focus on simplification. In this talk, we're mainly focused on fixing two things and then seeing also how they help us simplify code. There are notoriously only 2 features in the entire C++ language that every compiler has a tool, a switch to turn off. Every compiler. And in the case of the macro has exceptions, some standard libraries. And those are exceptions in RTTI. And in case you're not close enough to see the slides, that is not a love emoji, that is a heartbreak emoji according to Emojipedia. Because we love exceptions, but for some of us they've let us down. And we love RTTI, but for some of us they've let us down. And the problem is actually already on the screen. The RT in RTTI, what does that stand for? Run time. It's dynamic. There's that dynamic word again. And it's a feature where the data has to be available at runtime, a lot like .NET and Java metadata, in case anyone ever asks for it, even if they don't. And other languages are all in on that, and we only have it for one or two features, which is already better. But that's a symptom. And so I'm going to give you a sneak peek of the whole talk, so if you have to leave early to catch a flight, here's the spoiler. Today's exception handling requires throwing type-erased values. That means you're going to dynamically allocate when you throw. It means that you're going to do a form of RTTI when you catch. That's overhead whether you asked for it or not, even if you throw 42 and catch int. And RTTI requires binaries to store metadata, strings of type information, hash values of types, whether the program ever uses them or not. Now, you will find people who defend this saying, well, we can optimize this better, and they are perfectly correct. But you can't get rid of them by construction because some code might ask for it, so the information must be there. And those optimizations are really, I will characterize, they would probably disagree, but I will characterize as they're digging ourselves out of a hole that we already jumped into. Just a suggestion, how about not jumping into the hole unless we need the information, unless we know there's treasure right here in the field, instead of digging up the whole field and jumping into every hole. Oh, no, only the time that we need to get the treasure chest, we'll go and we'll dig there and we'll opt in. And so a pay for what you use principle to keep in mind for the rest of the talk, make things static, compile time by default. And dynamic is still there. We're not taking anything away from you, but it's only if you ask for it. And make it easy to ask for it, make it convenient, but dynamic by opt-in. Static by default, dynamic by opt-in. So let's take a look at the first part of the talk, which is about exception handling. The first thing to do is establish the problem, then we'll talk about what is an error for a couple of slides just to make sure we have in our minds what a runtime error is. And then I'll show the proposals that I'm bringing forward. And again, I should put a disclaimer here. I do chair the Standards Committee, but this is just me talking as an individual. The Standards Committee may or may not like any of this. I'm not speaking for them. But as I go through the talk, in a couple of places, I will show straw poll results as to what the committee does think, and I'll put context in it from the Cologne meeting 2 months ago about this proposal where it was seen for the first time in the full language evolution working group. But let's now first establish the problem. Let's say we have this function. What do you think of this code? Just shout it out. Two forms of error handling. Something unprintable, I think, but I couldn't quite hear. A fireable offense, perhaps? Maybe not quite that bad. But it's like driving, you're behind a driver who's white lining it and drifting a little, and your choices are stay behind them because you can't pass on the left or on the right or call 911. You probably want to consider the latter if you're in most countries. In some countries this is normal, so they know what to do. But they haven't decided, the author of this function hasn't made a decision that the author of a function has a duty to make. When I design a function or a class, part of my responsibility as a designer is to specify the error handling and decide on the error handling policy. Here, if I say, yeah, sometimes we'll throw something, sometimes we'll return something, I have abdicated my responsibility as a designer. Now, what's harder than getting your caller to do error handling? Getting them to do it twice. In two ways. Now this is a real problem because today we are bifurcated. Some libraries may return a widget error, some libraries may throw an exception, and how am I ever going to write templated code that can call either of these and do something sensible? Because in one case, even if this function this template doesn't handle the error just to propagate it. It has to know, do I do nothing and let the exception propagate because that's nice and automatic, or do I have to say if error, return error? I don't know. This is also an example why not agreeing on a common error handling policy means I am effectively bifurcating the community. I am effectively programming in a language dialect, an incompatible one, because I can't compose these two libraries easily in cases like this. So I took a survey, and this is the part of the isocpp.org survey. I talked about this when I gave this talk, this part of the talk at ACCU this spring. And about half of C++ projects ban exceptions in whole or in part. And these are the numbers from about 18 months ago. There was another survey done about 12 months ago. Notice the numbers are very much the same. And then the most recent one, which was done this spring, the good news is there are now, and this could be measurement error, we'll keep measuring this, but there are 3% more. Notice we went from 49 to 52%, 3% more that allow exceptions everywhere. But you might have noticed there are also 3% more that say they're banned completely. So that is not improvement, that is further bifurcation. You're getting less middle ground and more on the polar ends. And that's a shame, because if we ban exceptions, we're not using C++. And as I said at ACCU, that may sound like an ideological statement, but I think it's a factual one, not ideological. We're not using standard C++, because standard C++ requires the constructors that fail throw an exception. There is no other reasonable way to report errors, and it's what the standard library does. If you overload an operator, there's no space in the signature. The signature is defined by the language. If you're operator plus, you take two things and return a thing. Where do you stick an error code? You can't. So if you're in an F no exceptions world, you're not using constructors, you're using factory functions, generally, if they can fail. If they can fail, you're not using operator overloading, you're using named functions. You're likely not using the standard library, except maybe for the algorithms, because they generally don't throw. Especially if you've disabled bad alloc, most library functions, standard library algorithms don't throw, but you're not using the containers, at least not the standard ones. You may be in a divergent version of the STL that's not compatible, that does something else when exception handling is turned off. And this is fragmentation. Interestingly, when you take these same numbers and you look at them by the three kinds of error reporting that we polled, which was exceptions, numeric error codes, and sort of expected outcome result style types. One of the most interesting data points I found is that error codes have the strongest support of those three. That's the community voting with their feet. The expected outcome types, which are totally non-standard, even though some of them are in Boost, but many of them are custom, are allowed everywhere almost as much as exceptions, which are blessed in the C++ standard and have language support. And finally, perhaps most disturbingly, every one of these is banned outright in more than 10% of projects, according to these surveys. And that is a measure of how fragmented the world has become, because that means there are projects that cannot talk to each other at all, that cannot share code at all, at least not code that does error handling, and I hope that most of our code does, or aspires to. When you look at these same numbers, there's the original, there's 6 months later, and here's the most recent one from this year, you see a very similar pattern. So this is pretty stable across surveys. So standard C++ says we have exceptions enabled, we use constructors and operators normally, we use the standard template library, and then there's dialects, and there's not just one, there are many of them, because we keep inventing new ways to not use exceptions and to report errors some other way. And question, which of these does STD file system use? And the answer is 2 of them. So throughout the now standard file system library, pervasively there are overloads, one of which will return an error, and one of which will throw an exception, just in case you're in one of those worlds. The C++ community is so bifurcated that the standards committee feels they need to support both of these dialects, and they will probably not say it in those terms, but I will. We are supporting what is effectively becoming two languages, and that is not a good thing. And we have pressure to do this with our next round of libraries, like networking and other libraries that are coming to do the same thing, just so C++ developers can use them. That's a problem that needs a solution. And what's the root cause? Today's exception handling is not zero overhead. So summarizing the reasons as I've gone and surveyed people and teams over the last 5 years or so, and longer than that, but especially systematically in the last 5 years, I've been hearing the same 3 things over and over, 2 things and then an optional one. The first is, I can't turn on exception handling at all. And you ask them, well, why? It's standard. We recommend it. It's beautiful. But look what it costs. And they show binary size, or they show the other expense of it. Because just turning on exception handling incurs space overhead on every implementation, whether you throw anything or not. And this is regardless of whether you're using table-based exceptions or non-table-based exceptions. It is even with the optimizations that have been proposed and reported in this year's Standards Committee mailings. And this violates the first part of the zero overhead principle, which was, you don't pay for what you don't use. I should be able to turn on exception handling, and if I don't throw an exception, I should pay approximately 0. A nice round number, and we're not there today. The second problem is, okay, even if I have EH enabled, in certain code I may not be able to throw an exception, and you ask them, well, why? And there's 2 sub-reasons for this one. In real-time systems or memory constrained systems, where they have to be able to predict for a call tree, including for reporting an error, how much space and or how much time it will maximally take, so compute an upper bound on either space or time, or in some cases both. Can't throw an exception because I cannot statically compute an upper bound for how much space or time might be needed. And it's because I have to do dynamic allocation to throw and a form of RTTI to catch. Even if they're not in that kind of constrained system where the performance of the deterministic performance of exceptions is important, they may say, yeah, I could throw, but look, I returned an expected, and I can prove it's 100 times faster in my scenario. And that may matter even when people say, well, you know, you should throw exceptions only in exceptional circumstances. We're going to get a better definition in a few minutes, but that's not always true. You need to throw an exception when the function couldn't do what it advertised, and that usually is rare. But there are some functions that actually may fail often, and that is a legitimate failure. Imagine parsing XML, or parsing something that you got off the web. It may be quite common to say parse int, and like, yeah, that's, the word hello is not an int, sorry, right? It may be common to get errors. You may get errors in 10% of your calls, and you may not be able to predict where those are. This violates the zero overhead principle part 2. When you do use the feature, you generally couldn't reasonably do better by rolling your own. And then finally, the bonus problem is sometimes people say, well, I can't throw through this code because they may like the fact that exceptions propagate automatically, but not invisibly. They can't see, read their source code of their function and see the control flow paths because of throwing exceptions, whereas you can easily see all the others, the ifs, the whiles, those are visible. You can grep for them. I can't even see the exceptional paths. So that's something that people volunteered as a problem they regularly face. So these are the problems that I heard most often. When I presented this for the first time, I presented it to subgroups last year already, but this was the first time 2 months ago in Cologne where it came before the full evolution working group that's really responsible for recommending the design of the language. And I actually asked them to poll each of these complaints. I can't afford to enable it, I can't afford to throw, and I can't throw through this code because I can't see the code path. And we actually took a poll, not on the solution I'm going to show, I'll show those polls later, but just on, is this an important problem? Specifically, the poll was of the form. It said, for each one of these, is this a problem that is worth this committee's time to try to solve? You will notice that for all of them, there were some people who thought it wasn't worth the committee's time to solve them. But fortunately, the large majority of the evolution group felt, yes, these are problems that would be worth trying to solve. That doesn't mean we can find a solution we'll accept. But in principle, yes, we would like to invest time in solving these problems. So that's very heartening. Let's, for a moment, define what is an error. If you go to the dictionary, Merriam-Webster's a good one, they define error as an act that fails to achieve what should be done. So if you call a function that says parse int and you pass it a string, if it can't get you an integer out of that string, then it can't achieve what you asked it to do. That's a simple example. Basically, it comes down to, can the function achieve its success post conditions? Can it do the thing it advertises? And I'll say, let's use the term error, and to be crisper, a recoverable error, a program recoverable error, means a function couldn't do what it advertised. Only those should be reported as errors to the caller. And notice I did not say anything about it, whether you use exceptions or result types or error codes. This is a very general principle that is agnostic to the actual mechanism you use to report the error. You shouldn't even be telling the calling code about it unless it's in this category. This has some consequences. There are certain things that the calling code cannot do anything about. So abstract machine corruption is a very simple example. Let's say you use Stack Overflow. Not the online one, but actually really. Trying to make a stack array of 1 billion or something. Oops, that didn't work. If we treated that, think about it, if we treated that as an error code or an exception we report to the calling code, well, first of all, what on earth is the calling code going to do about it? It cannot programmatically recover, because you may be in a corrupted state. If you run out of stack, you may actually not be in a consistent state anymore because you might have spilled some of your writes or corrupted memory. But more to the point, if we did that, there would be no except functions. Every function could throw, because any function could be the last one who's got 1 byte left on the stack when you try to call it. So this is not a kind of error that we should report to the calling code, because the calling code can't do anything about it. And if we tried, we would do damage to our programming model. We'd be losing no except for all practical purposes, for example. So reporting that as a runtime error would really be a category error. It's not a runtime recoverable error. The same thing is true of a programming bug. So if we have an assertion in our program, or a precondition, or a postcondition, and it's a statement about the expected state of our program, if we're using assertions in that way, then by definition, if we violate one, what does it mean? It means the program is in a state that the code was not expecting and is not designed to recover from. Now, there are techniques for, if you can partition your memory and have memory isolation, and you can throw away parts of your program and restart them. There are techniques to try to recover, but it's not by normal stack unwinding and fixing things on the way back, usually. It's by abandoning parts of possibly corrupt process and then resuming, restarting. These also should not be reported as runtime errors. So out of bounds should never, ever be an error code or an exception. I know that that is going to raise hackles with some of you, because we're used to that. You'll say the standard library does that. I will show you that we talked to the standard library folks. I believe I have the polls in a few slides. And they agree unanimously, yeah, that's a problem, and we're going to gradually migrate the standard library away from basically the logic underscore error, which you might say is inherently a logic error that shouldn't exist. So here's our taxonomy. If we corrupt the abstract machine, we need to stop. We might, terminate doesn't mean right away. We might have some last ditch, try to save some state before we terminate, but we can't really continue. We have to tell a syshop or somebody like that, and we are telling a human being because we need more space. The program failed and you need to restart it. Category B, if there is a programming bug, like an assert violation or a precondition violation, we express that using assertions, log checks, hopefully soon contracts, and we tell also a human being, but this time we tell the programmer. This is category B. We want to come out in unit testing and system testing, and we've identified a bug. Please go fix your bug. Category B, we don't throw an exception because the program can't fix itself. We don't want to tell the code. We want to tell a human being. And finally, we have recoverable error, like host not found, or no, that string did not contain an int, please try again. And there we can throw an exception or use an error code, and we're reporting to a different species, to code, and the calling code should recover. So that's the taxonomy I want to highlight, because it's part of these 4 coordinated proposals, and it comes up when we talk about number 2 in particular, at number 3. So here are 4 coordinated proposals which are about trying to solve the problems we identified at the top. Each one of them could be its own paper, but I deliberately, and normally I encourage people to write narrower papers instead of big monolithic omnibus papers with a jumble of features. But this isn't just a jumble. These are related. It could actually be a problem if we tried to solve these problems in isolation, because we might get a local maxima. And we might say, oh, here's a solution for A, and here's a solution for B, and for C, and for D. And then you stand back and we've standardized it and lived with it for 10 years, and we realize, if we only had a time machine, how often have we said that? We'd go back, and if we'd actually thought about A, B, C, D together, we would have designed C a little differently, which was just as efficient and just as useful, but now it doesn't cause a problem with integrating with the other 3. So that's why I think it's important to look at these 3 together, and I think by the end of this section, I hope to convince you that if we do all of them, the sum is greater, the whole is greater than the sum of the parts in terms of what we get to achieve. So let's look at the first part of the proposal. The first part of the proposal, and the one that probably gets the most notice, is that we want to address the zero overhead of throwing exceptions. So inherently today, we are throwing objects of dynamic types that have to be type erased and dynamically allocated, and we catch using a form of RTTI. It's not dynamic cast that you can spell yourself, but it's an equivalent form that's built into the compiler that's basically a close cousin of dynamic cast that you can't spell yourself, except as catch base reference. There's a different kind of exception classification going on there. So the proposal is, well, if dynamic is the problem, static may not be the answer, but it ought to be the first place you look. So let's try to see if static is the problem to the solution to this dynamic problem. If we can throw values of a statically known type, that means we can return it by value. And if we catch by value, that means we don't need to allocate, and we don't do a heap allocation, and we don't need to do RTTI because we know its type. It turns out that if you do it this way, and this is basically the same as many languages have invented with a result type, such as in Rust and Go. Also, the same thing boost expected does, an outcome. If you do that, the result is isomorphic to error codes, but one of the benefits of baking this into the language is the language can basically overlap your success and failure returns and use the same registers or the same channel for either one, because it's only going to be one or the other. You're either going to succeed, and here you go, here's your int, or you're going to fail, and here's your error, right? And you can overlap those if you're the compiler, and that can be a lot more efficient. The thing is, we want this to be backward compatible. So because C++ already has dynamic exceptions, we want to keep all of the exception handling we have today in terms of the programming model, try, catch, throw. But we want to be able to opt in, therefore this is not a breaking change, to say, oh, by the way, for my function, Mr. Compiler, please go and implement this using the fast path, because I promise to only throw a stood error. So here's how it would operate. It's as if you return a union of success and error, and the Boolean discriminant could even go in a register or a CPU flag. That's an implementation detail. The idea is it can be made efficient. But the nice thing is we still have the exceptional programming model. We still have throw and catch. We still have automatic propagation. But we have the same implementation as error codes. It's just the compiler does it for us. So we're really doubling down on value semantics. You see how going static lets us double down on value semantics in C++. Just like we've done with every major release of the standard. In C++ 11, we doubled down on value semantics by making move a major part integrated throughout the whole language and throughout the type system. And that made our code faster, because we said, we're about values and we will optimize for those and we will embrace that. That's what this is saying. So now, from a sales point of view, let's put on our sales hats for a moment. Let's say you love this proposal as much as I do, and you want to tell someone about it, And if you're talking to somebody who loves exceptions, you can say, this is great. It just makes exceptions more efficient. It's the same programming model. You throw, you catch. But now all the unwashed masses who thought they couldn't afford it, now they can use it, and we've won them over. If you're talking to somebody in the aforementioned so-called unwashed masses who was using expected outcome and knew very well why they were using it because they couldn't use exceptions, you say to them, you know what? We're taking over the world. We're building expected and outcome into the compiler. Isn't that great? They're going to use it with their throw catch. Oh, and by the way, you know how when you use expected and outcome, you always have to write if error, return error, if error, return error? We can get rid of that and automate the propagation for you. So you're getting expected outcome baked into the language, but better because you don't have to automatically propagate it. The compiler will do it for you. If you're talking to a C programmer who says, you will never take my return code out of my cold dead hands, you'll say, it's okay. What we're doing is we're convincing those newfangled C++ people to adopt error codes. We're really automating error codes. They just don't know it. It's giving a nice syntax. It's just a syntactic sugar for error codes. By the way, you know how when you use an error code and you return an error code, when you use it as a return value, you don't get to actually have a return value? And they say, well, yeah, that's kind of annoying. And so what if you do want to return a result? Well, I pass it by an out star parameter. Yeah. So what if you have a return value and you want to add an error type? Well, then I add an error code star parameter. Yeah. Yeah, I know. Wouldn't it be nice if you didn't have to do that? Wouldn't it be nice if you could just return your result or an error and the compiler did that for you and you didn't have to have these out parameters? So you didn't have the error code type monopolize the return channel. The compiler folds them for you. Oh, that's pretty good. Oh, and by the way, we'll propagate them for you so you also don't have to write if error, return error all over the place. Now their eyes start to get warmer and barriers start to break down. So here's the core proposal summary. The dark green, the try-catch, no change. This is still C++ exception handling as we program it, as we know it. The only thing that's different is the word throws on the function f and function g in this example, where the function is opting in to say, by the way, I may fail, but when I do fail, I may not always fail, but when I fail, I will throw a stud : error type, which by the way is trivially copyable and movable. It's actually even a little bit better than that. So to throw, I need no dynamic memory allocation. I can bit-blit it all the way back to wherever it's being handled, even if it has a non-trivial destructor. See the paper for the magic and see the other related papers. This is not just a bit-blittable pod type. This is a type that could have a destructor, but I don't know how to bit-blit move, so that if it does have one at the catch side, I can destroy it properly. It's totally type safe, but totally efficient. No allocation, no RTTI. Still with destructors. We're doubling down on value types. And for compatibility, let's say I call something that like return quote xyzzy quote s. Now that is a string literal that is a stud string in the standard. And then I add plover, another string. So I'm creating a temporary stud string object and I'm returning that. If I call something that could throw something else, because that string concatenation could throw, I can translate that into a stud error. And we'll see where a particularly bad alloc we would like to treat differently anyway, but bad alloc isn't going to go away. It's just going to get greatly reduced, we hope. But this applies to all of the standard errors. So we can still call existing code that uses dynamic exceptions, but if they throw something and we don't catch it, that's fine. It still propagates automatically. We'll just convert it to a stud error. So they would have still had to allocate it and incur the cost they had, so no change to their status quo. But as soon as it hits us, we are adding no extra overhead. We just zip it right along. That's the model, and it's fully backward compatible. It does not require change to the ABI. It does not require change in the semantics of any existing function because you're opting in, and then we can take the fast path, and it converts to and from as you cross boundaries from the old style exceptions to the new style functions that use the new style ones. So because of this, because it is isomorphic to error codes, it has all the overheads of error codes, which is minimal, typically constant time, And it's deterministic, because with error codes, we have static tools that can compute upper bounds on how much time it may take to return an error code. Those, I still need to validate this with implementation. My expectation is that with very minimal, if any, adjustments, those will directly work with these exceptions, whereas today we do not have tools that for today's exceptions can compute upper bounds. But we will for these. Why? Because they're isomorphic to error codes. By the way, a nice trick when you're designing a new thing, if you can say it's isomorphic to something else that is well known, and you're not just saying it, it's actually true, you can demonstrate there's an isomorphism, right? Yeah, I see here the chuckle, yes. Okay, sales hat off. Yeah, I forgot to do that before. Technical hat firmly back on and over the ears. If you can show it's isomorphic to something else, all your proofs just come right over. Everything that was proved about that is now true for you too. So there's a great power in saying it's isomorphic to error codes. So in pseudocode, to summarize, here's what it looks like. On the left, to throw a my exception, I have to essentially new up. You can do this a bit more efficiently, but essentially new up. I need some sort of dynamic allocation that is not stack allocation. And if you're thinking, but Windows does it on the stack, no it doesn't, see P0709 appendix. It cheats by using stack memory and interfering with the stack by using a weird stack-based allocator that will make you run out of stack faster, but it is not a stack allocation. It is not alloc. So you need a dynamic allocation, and then at the catch side at the bottom left, you need to do a form of RTTI to say, is this void pointer a base star? You need basically a dynamic cast that goes from a void star, which dynamic cast, the standard one does not do, to a particular base pointer. Whereas the proposal on the right-hand side is simply return a value that is basically 2 words, return it by value, and catch it by value. And that's where the efficiency comes from. So what are the benefits? I hope, if this succeeds, and this is a long-term thing, like please do not ask, is this in C++20 or C++23? This is a long lead endeavor that is still in its early phases. We still have to, for instance, do a prototype implementation that does not yet exist. Not a full one anyway. But we hope that what this will achieve is that there is no longer any valid technical reason not to enable exception handling of this form, even if you still disable the old exceptions. You may still disable dynamically typed exceptions, but there should be no reason anybody ever asks their compiler vendor for a switch to turn this off, because it's zero overhead. And it hopefully will let all code report errors using exceptions, even real-time code, even embedded systems that are very space constrained, because I can't reasonably write it better than this. Even if I'm using a C error code, and C developers, one of the things that I do like about C, I don't use it regularly, I use C++ because I like it better, but one of the things I like about C is that you see what you get. You can see the costs of things to some degree. You still, memory allocation, et cetera, the memory hierarchy is still opaque, but the costs of things are more visible than they are in C++. But even in those, for those C programmers, we can do better than you can do by hand because you can't fold the error code and a meaningful result into the same return unless you return a union all the time and do your own discriminant. Like, I mean, you have to do a lot of work by hand to get an equivalent semantic. So no, it fails the test of you can reasonably write something better by hand. And then we get, if we can get to this, then we can get to the bottom part of that pyramid that I was proposing, and we can get to an actual simplification in teaching. We could start to teach a rule as simple as every function should be declared with exactly one of no except or throws, all new code. This has happened before. As the last bullet says, we now teach, now that we added override and final, we can do something we could not do in C++98. We can, and we do in the core guidelines teach, that every virtual function should be declared, whether it's in the base or derived, should be declared with exactly one of virtual, override, or final. And you can show that this, people can argue about styles, hey, yeah, but I'd like to say to, but you can show, no, you don't need to. This is perfectly clear and consistent. The same thing can be true of exception handling, that you have to write just one of no except or throws. And that's a simplification in the way we teach C++. But now let's look at the second and third parts of these coordinated proposals, because these are about throwing fewer exceptions. The fact that's on the screen is actually language independent. Go has discovered this. .NET and Java, all of them have discovered this. Here's a quote from Joe Duffy, where he points out, who's a .NET expert, and worked on a systems version of C# that was used within Microsoft for a while. And he pointed out that, once you have contracts, and this is irrespective of language, but he specifically ties it to Java and .NET, something like 90% of all of the exceptions specified in the Java and .NET standard libraries become preconditions, and you don't throw them no more. Remember, if an assertion or precondition fails, it indicates there's a bug in the program, so you shouldn't be reporting it as a dynamic error to the calling code as if it could do something to recover. It can't. By definition, your program is in a state that that code was not intended, not designed to handle. Instead, this should be happening during testing, and you report it to a human being, the developer, and say, please go fix your bug. And that means that it can get rid of something like 90% of the exceptions in Java and .NET, and the same thing is true in C++. So the summary of the proposal is, as I alluded to before, in the standard library, let's actually, with a transition path, because this is a multi-year, multi-release transition path, start, and especially for new things in the library, start moving to a world where we no longer make preconditions throw exceptions. And if we do that, suddenly many functions in the library can start becoming no except. And so far, the Library Evolution Working Group is very strongly, in most polls unanimously, behind that direction. And so the uses of stood logic error should eventually turn into things like assertions or preconditions or things like that. But it's a long migration and with compatibility in mind. And that brings us to the third part. What's odd here? When I first saw this, I thought, it's kind of odd that this astronaut is playing their guitar in a vacuum. But if you think about a fictitious scene, which maybe isn't the most productive thing in the world, but if you think about this fantasy scene, there's no audience, so that's okay. And the guitar is in physical contact with the suit, so it may not be a very clear audio, but they can probably hear the guitar. And then in their microphone, maybe the audience on Earth can hear. So yeah, okay, you can squint and make that make sense, but it looks kind of odd. Similarly today, here are two oddities, numbered 1 and 3, because they're oddities. Oddity number 1 is exceptions must be dynamically allocated. Today, we talked about that already. Oddity number 3 is that dynamic allocation failures are reported using exceptions. What's wrong with this statement, with putting those two statements together? Actually, two different things. The first is, well, we already saw it would be nice if exceptions didn't have to be dynamically allocated, so we already addressed that part. But also, many allocation failures don't need to be reported as runtime recoverable exceptions. For example, if you knew int 1,000,000, or let's say char or byte, that's because that's a better raw buffer. Let's say you knew a buffer of 1,000,000 bytes, and that fails. Does that mean you've exhausted the limits of the machine? No, you can still run normal code. In fact, you might say, okay, give me a buffer half that size and let me try again. You might do fallbacks. So that doesn't necessarily mean that you've corrupted your machine. But if you try to do new of a single int and that fails, you are in deep, deep trouble because you have pretty much exhausted the abstract machine, the actual machine. You may not even be able to return from the function, which means you can't throw an exception or return an error code reliably. Why not? Because to return means first, before you can even deliver the error code or the exception, you have to unwind by running the destructors. Destructors are normal code. Normal code often allocates. Unless you know that nothing, not one of those destructors or anything they transitively call down to a million function calls deep will perform an allocation, you have no guarantee that you'll even be able to return. So you cannot continue executing. And so termination semantics, anytime I say fail fast or termination, sure, you'll want to have a fail fast handler, a last ditch, let me flush what I can to disk and hope for the best, to prevent data loss. But I can't just continue on as if I can recover from this and nothing happened. So where we are now is we think we've addressed the first one with having lightweight exceptions. But so now what do we do about memory failures? Sometimes I'll say out of memory, and that's fine, but that's a shorthand for a broader term that is allocation failure. So sometimes people will rightly say not every failure to allocate really means I'm out of memory, and that's true because there could be fragmentation. It could be just that particular allocator or pool is full. It could be because it was a big thing and you're trying a big buffer allocation request and you can try a smaller one. But I think we know that when we say So sometimes I'll say is a shorthand for all of that, but a more technically correct term is allocation failure. So the direction from the Cologne meeting 2 months ago is one that I actually strongly agree with. It was not the proposal I walked into the room with. It was one of the alternatives that we had talked about, but it was not the one I walked into the room with. I think it is way better than my previous idea. So thank you, Library Evolution Working Group, because I love that old say. There's that, is it from South Park? I've never seen South Park, so I only see the memes. I think it's from there, that none of us is as dumb as all of us. Yeah, that's fun to say. None of us is as smart as all of us. So this proposal would not be as good as it is without the help of many, many people, dozens of people acknowledged in my paper. And certainly here, I did not come up with this very simple and nice idea. Thank you to Niall and Titus and many others who came up with it. The idea is, let the allocator decide. We're going to have allocators advertise in a no-except queryable way, so it's part of their static type. Hey, if I can't allocate, do I fail fast or do I report the error? Throw bad alloc. That's all, simple idea. And then add a conditional no except to every function in the standard library where allocation failure is the only possible failure. And if you're using a fail fast allocator that doesn't report, that function can be no except. Now you have great control and can make large parts of the standard library no except as actually used in the field. And that leaves only one major question. What about the standard std allocator that everybody uses by default? Like when you have a vector of int, you're implicitly using std allocator, which uses global new, basically. There are several global news, but as a shorthand, I'm just going to say the default global new. The third poll that was taken, actually second in order, but the third I'm showing on the screen, is, okay, so now we categorize these two kinds of allocators. On allocation failure, they either fail fast and abort, or they throw bad alloc and report the error. They're aborting or reporting. What should the standard one be? Library Evolution Working Group with only one weakly against. These numbers are strongly in favor, weakly in favor, neutral, weakly against, strongly against. Except for one person who was weakly against, that group that day was unanimously in favor, minus one person, of changing the global default on everybody, even though that would be a breaking change. Does that scare you or delight you? Applause for if that scares you. Okay, applause for if that delights you. This is a good, if you'll pardon me a tangent, we'll come back to this in a moment. This is a very good place to use an object lesson to give an illustration of what consensus means. We just had roughly by decibels, the AV people could probably measure it accurately, I don't know, something like 4-to-1 in favor of, yeah, this delights us, let's go do it. But if we just did that, we took that result and said, say this was in the committee and we were deciding it, we took that result and said, great, it's changed, and we run over those people who clapped first, that is called tyranny of the majority. You can do it, but it's not consensus. So sometimes people ask, well, what is consensus in ISO? It is not tyranny of the majority. It's not because you got the votes, even though that's greater than the 3-to-1 in favor that we usually look for. It also includes the absence of sustained opposition. So the majority is required to listen to the minority. You cannot just take a vote and say, I won, terrible to be you. No, you have to listen to the concerns of the minority. You have to actually try to change the proposal to satisfy their concerns. And now, if after you've tried that, you can't satisfy their concerns, then you take a vote and it's 4-to-1 and you win and you go home and you do it anyway, but not without first listening to them. So that's the first of the two parts of consensus. It's not a tyranny of the majority. The second part is it's also not a tyranny of the minority. The minority can object and must be listened to, but after they have been listened to and a real solid, sustained, good faith effort has been made to take into account their objections, and then the majority still decides, no, we just can't do that. They've been listened to. They cannot veto it forever by simply saying, no, we have to have unanimity. That would be tyranny of the minority. So it requires a real collaboration and a real amount of work so that it's not just a numerical thing. So sometimes people will ask you, what's the numerical poll? And the numerical poll matters less than the effort to converge and to work together to solve the problem in a way that addresses sustained opposition. So sorry for the diversion, but it's something that I live all the time in my job as chairing the committee. And it's something very important to how the committee operates. And so it was a nice lesson. So those of us who clapped for this, coming back to the slide, Library Evolution Working Group agrees with you. Those of you who clapped first saying you're kind of uncomfortable, Evolution Working Group, half of them agree with you. And so the Language Evolution Working Group was split right down the middle on this poll, which would be a breaking change for existing programs. Now, if you think about what this means, if we suddenly start saying that global new fails fast by default, you can argue that's not actually a breaking change for most programs. And the way you argue that is as follows. Most programs today, and I say this with more words in the paper and examples, but most programs today already aren't safe for a bad alloc. They aren't. Some are. There are programs, there is code that is safe for allocation failure. But most of the code you think is safe for allocation failure, when you actually look, like a super common result, way over 90% of cases I've seen personally and worked with people, they're sure their code is right, and then they realize, that code couldn't even have executed. We never even tried that path. Why did they get away with it? For reason number two, why this is not really a breaking change for many people, is because bad alloc almost never happens in practice. If you're on a lazy commit system allocator, unless you have specifically worked with your user commit settings, say on Linux, or you're using a pool-based allocator that can throw an exception when you exhaust that pool, you can go decades and never actually see a bad alloc, even if technically it could be thrown. If you're on a system that has virtual memory, you may thrash and run slower and slower and slower before you ever get to the bad alloc. You'll be not executing your program. Overloaded the word executing. You'll be killing your process. However, so you could say that many wouldn't even notice. Okay, let me give just a couple of anecdotes. So I actually created with Marshall Clow and the help of others, but especially Marshall, after ACCU, we talked about this. And on the plane ride home, we created something called BAB, B-A-B-B. You can find it as a project on my GitHub. It's a repo under github.com, Sutter, or Herb Sutter, I forget. Whatever my handle is on GitHub. And the point of it is it's a very simple little fault injector that you can add to your global allocator or to your custom allocators that will inject random faults with a determined frequency and profile. So I asked the PowerPoint team, well, first of all, I asked the compiler team to say, could you try this and see if, the Visual C++ compiler team, could you try this and see if it finds any errors, like where throwing a bad alloc that we inject at an allocation point to make it appear to fail might take down the compiler. And the answer was, no, we can't do that. Of course it'll take down the compiler. We don't even try. So, oh, okay, well, what should I do? Well, you might try the libraries team next door, literally next door, the next team room over. So I walked to the next team room over and talked to STL, who might be in the audience here today. And I said, so can we try against our standard library and instrument it? And he said, well, we might be able to do that, but I don't know what you'll learn from it because we don't, I mean, the standard library implementations are probably the most battle-tested, exception-hardened C++ code in the world. Well, I wouldn't be surprised if we just fall over. So I tried. I went home that afternoon, created a new project in Visual Studio, created, LinkedIn included bab.h, and all I did was create a test loop which did pushback into a vector of string and ran it with random faults being injected like once every 1,000 allocations or so. See the paper for the longer story. Short version is it fell over, it crashed. Even though it should, even though it threw an exception and there was a try-catch block around the vector string pushback loop, the exception never made it. Why? Because you might need to allocate to throw an exception. No, it just fell over. And I did not get to try any other examples with libc++ or libstd++. That example worked on those implementations. But that to me was strong data that none of our customers who ever build in debug mode and use the STL are actually hitting bad alloc ever. And I know that because the actual root cause is something that is on by default in our debug mode /OD. And it is something we know from telemetry that 90% of customers do not turn off. So we know if you're, 90% of you, if you're using Visual C++ and you're running in debug mode, you would be in this situation. And we have had like, I forget the number, it was like 4 or 6 bug reports in the last 3 years about this. Hard, but it's the very first thing I tried. Vector of string pushback just falls over if allocation fails. That is data that people don't write bad alloc hardened code, or they would have been testing it. In fact, the bug reports were people who were testing for bad alloc hardening. And most of the time, people aren't encountering bad alloc in the first place. So that explains why Library Evolution Working Group was willing to take this change, because I think a lot of people will just never notice because it just doesn't actually happen, but it will let us make a swath of the library no except. But then we come back to the first group who applauded. There is code there that relies on this behavior. And so the updated proposal I'm going to make is basically the same thing, except instead of saying unilaterally that the default global and standard allocators fail fast and abort on failure, make it a configurable option to let the programmer decide for their whole program what they want the behavior to be. That way it is not a breaking change, but anyone who wants to adopt the new behavior can start seeing no except performance improvements in the standard library as we roll this out, if we go this direction a few years from now. So that's where we are right now. So it looks like that's a path we're going to go to, but it's going to require to make sure we just don't break the world, because that would create hard opposition. Even if it's minor opposition, that's important. So I think just a switch to let the programmer decide which kind of allocator the global allocator should be enough here. So our taxonomy, we can extend that saying a failure aborting allocator is considered in category A, corrupting the abstract machine, and a failure reporting allocator, well, it reports errors. So what are the benefits? Well, we talked about turning preconditions from exceptions into static bug reporting to the developer, and putting these two things together, taking assertions and preconditions and much out of memory allocation failure, and making them not be exceptions, will eliminate something like 90–95% of all exceptions there are, and will let us make most code, most functions be no except. And that is a performance carrot, because no except does. I know you're going to hear people who say it doesn't. You can go out and bolt it. It does make your code faster. As a bonus, it will eliminate about 90% of those invisible control flow paths, because those are the exceptional ones, the ones that are hard to reason about. And if you look at Guru of the Week number 20, I showed a 4-line function with 3 normal control flow paths and 20 exceptional invisible ones. We can do a great simplification by getting rid of many of those invisible ones that makes our code cleaner, easier to reason about, and more robust. Finally, in the exception handling section. What about supporting an explicit way to see where my exceptional paths are? So if you are familiar with Swift, or if you looked at, Go doesn't have this yet, but they recently announced that they're working on it. Many languages have this idea of, at the call site, to write a word, like in the Go proposal, I think is checked. In Swift, it's try. Here, it's try. On the expression or statement that calls something that might throw. If I do that, notice that exception propagation is still automatic. There's no catch here necessarily. It's just saying I'm annotating with the word try to signal in the source code, oh, I can now see and grep and reason about this line of code may have an edge out of the function. I can reason about my control flow. Now, today, we could not possibly, even if we add this to the language, we could not possibly require it. Because almost everything can throw. That's the default. That would, if we required people to write try on everything that could throw, there would be mass rebellion, and there would be a new switch among the first two for exception handling and RTTI saying turn off the try requirement. Because you'd be writing it on almost every line of code, and it's like highlighting every line on a page in a book. It defeats the purpose. Nothing stands out anymore. All you have is a yellow or a green page now that makes the text a bit harder to read. But if we are in a world where most functions don't throw, and certainly as it says in the text bullet in the middle, if we required this in new code in such a world where you didn't have to just annotate every single function call, now we could get to a world where we could actually give compile time guarantees that if there's no try or throw, there's no exception. And that's a very interesting place to go. So what are the benefits of this? Convenience, we still get automatic exception propagation, no change to that. We're just making it visible in a lightweight way so we can see the paths where the exceptions might go. And if you put all these four things together that I've just said, 2 and 3 enable that most functions are no except, 2, 3, and 4 together enables us to require writing the word try every place that could throw. Now I could take C code and compile it as C++, and either I manually or a linter tool could immediately, a compiling tidy tool could just put try in the things that could throw. Because one of the big objections to taking C code and compiling it as C++ in a C++ project is now it's probably not exception safe. It's C. It was not designed by the author of that code with exceptions in mind. It's not probably doing RAII. This is a language with no destructors. It probably has its F close without a catch because there's no catch, right? So if I take that C code and I can compile it as C++, but like today, but now automatically putting in the word try at all the places that could throw, and that's the minority of places, now I can actually look at that code and reason about whether it's exception safe or not, and know where to look to do tweaks to fix it, to make it exception safe if it's not. I can now migrate, converge C and C++ code with more confidence. So I showed at the top of the screen, the top right, the polls on these 3 problems. Are they problems worth committee time to solve? The committee agreed, yes, this is worth committee time to solve. That's not the same thing as saying that we'll like your particular solution to that problem. So for the things that I've just shown you, I've already shown you the votes for number 2 and 3. For number 1, enabling the throws declaration to have the efficient value-based exception handling, there was large support, still 9 people against, but there was large support for continuing to pursue that direction, which basically means they said, no promises, Herb. We may not ever accept your proposal, but we agree you should do more work. Just to be totally clear, that's what these votes mean at this stage. But it was also implicitly a promise that if you do it, we will look at it again. So it was encouragement, but not a promise that they'll ever take it. For number 4, there was not consensus. There was mostly opposition to try expressions. And so I may decouple that from the proposal, and that can be separated, but I'm still going to design the whole thing, all 4 of these parts together. They just may not all be adopted at the same time, or some parts may not be adopted in standard C++ in the foreseeable future. We'll see. But the core of the proposal, numbers 1, 2, and 3, seem to be going well. That's a status update for that. Now we're going to talk about a totally unrelated thing using almost the same slides, because it's the same pattern. First, we established the problem. Today's RTTI. Notice how I just changed EH to RTTI? If you compare slides, they're identical. Violates the zero overhead principle. I can't afford to enable it. Means because I'm paying for what I don't use. I can't afford to use dynamic cast. That used to say throw an exception, but it applies to dynamic cast because I can write in a more efficient one by hand. So here's a code review. What do you think of this code? Anyone? Say again? Should use a reference. Okay, but this is supposed to work with pointers too, right? So if you want it to be null, there was another comment in the front? No? What's wrong with the code, even using pointers? Static cast because it's a downcast. Emojipedia does not say that this is called downcast. It just calls it sad face, but it should be called downcast because that works better for this talk. Wait, that's an unchecked downcast. Nobody would ever do that, right? How many of you, not outing yourselves now, but how many of you know somebody, like maybe a friend or colleague who might have written something like this once before? Keep your hands up if it was you. No, just kidding. If you were in the talk by Joe and Shane on Wednesday, and thank you, Joe and Shane, for letting me use this slide, they were talking about a different part of the security vulnerability landscape. One of the things that we've discovered that I've learned over the last 5 years or so, and I've been thinking about this particular problem for the last 5 years and trying to make dynamic cast more affordable, because we hear about bounds problems as a source of security, vulnerabilities, buffer overruns, and so we should do something about that. We did. We standardized span. So don't use pointer arithmetic, always use span. It pretty much solves bound safety. And things like don't reinterpret cast to a larger type, which also is a way of going over bounds. And some of these vulnerabilities are about use after free. So see my previous talks, see the lifetime profile, which is now being upstreamed into Clang and has already found bugs in Chromium and LLVM. Thank you, Gabor and Matthias for your help there. Kyle, Neil, and those who have helped with that. But I'm going to focus on a different part of this chart now. Notice type confusion. Type confusion vulnerabilities. Now, these are security exploitable problems that can cause an attacker, whether a bored kid or a nation state, to use your machine for things you did not want and to do bad things, right? They can hold it hostage, they can sit there for a long time, all the stuff that Black Hat conferences enjoy talking about. Type confusion in particular includes several things, but one of them is downcast from base to derived, except guess what? It wasn't a derived. Ha ha ha, isn't that funny? Well, no, it's not. When an attacker uses that to cause an exploit, and that damages the reputation and the security in fact of C++. That does harm to our reputation, but also harm to our use of C++ in fact. And here you'll see that in the middle of the screen, it's a not insignificant part. Not all of those 152 vulnerabilities, known vulnerabilities that were identified in the last 2 years that were type confusion were static downcasts, but a good chunk of them were. Where, in fact, what happened was, going back a couple of slides, in fact, that is exactly what the code did. The vulnerability was caused, a large class of those, by doing essentially a static cast, downcast. Well, why would otherwise smart people do that? Well, as shown in the smaller sub-bullets, I found, as I talked to these people, a couple of patterns. The very first one sounds a lot like the exception handling one. Well, I can't use dynamic cast because RTTI isn't enabled, because it's too expensive. Just turning on RTTI, even if I never use it, even if I never use type ID or I never use the dynamic cast, bloats my binary size, and look, here are my numbers. I can prove it. In fact, RTTI is essentially banned in Windows for that reason. Exception handling is being allowed more, but RTTI is banned largely. The second category was of people who did have RTTI enabled. So they already had the binary bloat of their executable, so that didn't bother them. But they didn't use dynamic cast because dynamic cast itself was too expensive. And I know some of you will say, but we know that Microsoft's implementation does string comparisons. Yeah, we're fixing that. But it wasn't just that. It's also on other implementations that people were doing the same thing and saying, no, I can't use dynamic cast because it's too expensive. And then many of them did say the same thing at the end, which was, and we tested, so we knew the downcast was safe. Remember, we're having this conversation because this was an exploited security vulnerability? No, it wasn't safe. You may have tested, but it was still a bug. Oh, and by the way, if you look at the ISO CVP survey from this year, about a third of projects ban RTTI in whole or in parts of their projects. So the fragmentation is not as great as with exception handling, but it's still very significant. This is not a trivial part of the community. And again, if you bucket these by dynamic cast, a virtual query like a COM query interface, or just something custom like a type tag that people often invent when they can't do their own dynamic cast, and you say, how many of you are allowed to use each of these? All of the non-standard methods like COM and custom type tag I rolled by hand last night are allowed everywhere, only a little less than dynamic cast. They're widely permitted. And the worst part, this is the place where this is worse than the story of exception handling. Remember, with exception handling, a great measure of the fracturing of the community was that more than 10% of projects banned each one of them. Like every one of them was banned by 10% or more of projects. With RTTI, it's 20% or more. Every single one of these is banned in 20% or more of projects. This is an even greater fracturing. So again, this violates, it's because RTTI violates the zero overhead principle in two ways. People say, I can't afford to enable it because just turning it on incurs space overhead. And then they say, well, even if it's enabled, I can't afford to call dynamic cast because I can do better by hand. And that violates, don't pay for what you don't use, and it violates, when you do use it, you can't write it better by hand reasonably. Again, it's the zero overhead principle. The language violates it, and so users vote with their feet and say, no, we're not doing that. So what do we do? Type information is not bad. I like type ID and type info. What I don't like is that all of their information gets baked into my executable whether I ever look at it or not. I want it when I want it. So again, if your problem is dynamic, that doesn't mean that your solution is to use something static, but it's a good place to start, so let's start there. Prefer static type information. The first observation is once we have static reflection, which is making its way through the standardization process, and perhaps a few years from now, it will become more commonly available, we don't need runtime type information at all. It is totally subsumed, totally obsoleted by static reflection, which gives you much more information than the runtime one does. And before you say, yeah, but the runtime one is available at runtime if I need it, what can you do with any static information? Store it somewhere, and it's dynamic information. And in fact, as soon as you say, yes, as soon as we have static reflection, you can easily create, pretty simply create your own runtime dynamic reflection. In fact, I did not know this until his talk, but Andrew Sutton in his talk on Wednesday mentioned that, yeah, in the last 2 weeks he wrote one of those. Because once you have the reflection, and he owns one of the major reflection prototypes so he can do this, once you have the reflection information, all you need to do is store it somewhere. And now it's runtime available. But you only get the things stored at runtime that you asked for at compile time, so you only pay for what you use, what you actually use. So the proposal to solve this part of the problem is, I believe we should adopt static reflection and compile time programming, both of which are already in progress. And then we could just get rid of type ID and type info, but I think type ID and type info are not bad. Like type info can give you a hash, that's useful, but make them const eval, make them available only at compile time, and if you really want the value at runtime, store it. So The second part is dynamic cast. It's also great when you need it, but dynamic cast is really powerful. It can cast across inheritance hierarchies to sibling bases that are otherwise unrelated, but happen to be inherited by the same derived type. It can navigate virtual base classes with ease and do backflips at the same time. It's also super expensive because it can do all those things. And if you ask for a dynamic cast, you are asking for the ability to do all of that. Just like we tell people, if all you need is the lower bound, the lowest value in an STL container that has this value, don't ask for the equal range, which gives you the lower and the upper. You're asking for more work. It'll be slower. Same thing with dynamic cast. If all you need is a downcast, don't ask for a dynamic cast. It'll be slower because you're asking for more work. There's a sweet spot, I think, and this actually hits all of the type vulnerabilities that I have seen that were root caused by not using dynamic cast. If you are need a downcast that doesn't cross a virtual inheritance link, so there can be virtual inheritance above or below you, but you're not crossing in between the base and derived, there isn't a virtual inheritance link. Turns out we can implement that super efficiently. And here I'm going to present other people's work, not my own. My contribution was just to say, seems like that should be able to be done faster. And then other people pointed out, yes, we've been doing it, here are our results. And so I'm pleased to report their work. So here is work done by many people, but particularly by Peter Collingborn, Kostya, and Joe, and Jim. And I'm going to talk about the Windows cast guard, but it is derived from Clang CFI. So even though I'm giving the Windows numbers, kudos to the Clang folks, to Peter, Kostya, to everybody who worked on the Clang CFI. It's super compatible. You don't have to change the ABI, don't have to change vtables, doesn't use RTTI. Everything I'm about to say works with /gr- on Windows with no type ID, type info support. You do a simple range check. You saw the code earlier. The way it works is the super smart insight, and I think the primary person here is Peter Collingborn for this insight. Thank you, Peter. Is that if you take your vtables and you don't change them, but you arrange them in memory in a certain order, then if you are given dynamic pointers to two objects, you can look at their v pointers and know just by doing a range check on the v pointers if the hopefully derived object's v-pointer is in a certain range, is in the range of all the vtables of types derived from that base. With a simple bounds check on the v-pointer, which is constant time and requires, in general, 2 memory accesses, one of which is likely already in cache, you can compute in 5 instructions and 2 memory accesses whether the downcast succeeds, with perfect type safety and fidelity. This is a very important result. Now it's intra-DLL, so it doesn't work across DLLs. The preliminary results on trying this with spec and with Windows is that there is very low impact, negligible impact on binary size and on runtime. The highest overhead we have measured so far, or that Joe has measured so far, one of Windows' largest DLLs is 1.5% bigger because of checks performed in function calls, injected checks. Because the current one, all it's doing is saying, oh, I notice you're doing a static downcast. I'm going to inject a check for you. So you don't actually change the code to down_cast. It's just noticing you're doing a static downcast and injecting a check. But that 1.5% is not compared to RTTI. It's compared to doing nothing at all. It's compared to static cast, because RTTI isn't even allowed in Windows because of the binary bloat, and dynamic cast, I should say, in particular. So the proposal for standardization that I would like to propose is to provide a way to ask for only what you want. Cast down from base to derived, not across a virtual inheritance link, and then I can know at compile time and give you an error if you don't do it, because I can statically know whether you're obeying, whether you're in that sweet spot. But if it compiles, it's guaranteed to be 5 instructions or so, which is way different than today. And you don't pay unless you use it, and you cannot write it better by hand. For example, Joe did a test for a simple single inheritance hierarchy where he instrumented dynamic cast, And we can quibble about whether it's the best possible dynamic cast, but this is just actual data from the field. And he did an instruction trace. So this isn't source code. This is going through just the instructions actually executed. And the dynamic cast was not this, not this, not this, but there. It was that many instructions. The cast guard version was this much code, most of which is comments, and I'll let you see it a bit better now. So the first two instructions, so the first half of that, which is all comments and two instructions, as you see in the comments, is a null pointer check, which we would have already done with static cast anyway. So that is not overhead compared to static cast. So you can already ignore the top half of this. What remains is 5 instructions where I load 2 v pointers, basically, and then I do a range check. I do a sub, comp, jump. That's it. If we can standardize a downcast that people can use, then we're in a world where there is no valid reason not to use the standard cast that is type safe and is 0 overhead, don't pay if you don't use, and you cannot do better by hand. So this talk has been largely about fixing things, fixing exception handling in RTTI. Sometimes it's a bit about adding a knob, but it's adding a knob like throws to an existing thing. It's not like inventing a new thing like concepts, which is the add things bucket. But by fixing things, we can simplify the programming model and the language. And I'd like to suggest that the right-hand side is a future worth considering. If we inverted this pyramid so that in the future we had much more emphasis on simplifying the C++ we have, and also on fixing the C++ we have in ways like I talked about today, is that something that you would like to see happen with C++ evolution? So we're going to try, and I will try to convince more people that especially the simplify part is worth doing. Remember, a really good rule of thumb, static by default, dynamic by opt-in. That gets you to don't pay for what you don't use, and when you do use it, it's as efficient as you could write by hand. That is C++. That is C++ic, so to say. And like it says in the top right, our historical strength is static, and every time that we have added a feature in the last 20 years that has markedly improved the language, nearly always it has been doubling down on our static nature. Concepts for static typing, templates for static polymorphism, and now static exception typing, static RTTI with reflection. So let's make exceptions in RTTI more affordable and usable. Let's actually do work to fix C++. It's no wonder that the only 2 features in the standard that are not 0 overhead are the ones that every compiler has a switch to turn off. People are voting with their feet. Let's fix it and unfragment the community. And then also, besides fixing things, as we go into the future and in later talks in later years and later CppCons and other conferences, I would love to see more talks, more proposals about actually aggressively simplifying the language that we have today to get rid of pitfalls, get rid of corner cases. And the more we can do that, the more we can benefit C++ now and in the future. Thank you. Questions? I know you, John, I know you want to make some announcements. Do we have any time for questions? Take 2? All right. I'll take one over here because I know who you are and you're on the committee, so I'm sorry I'm gonna downvote you because I can only do 2. Sorry, Peter. I'll buy you a beer later.
So you talked about the static library being able to add no except in a lot of places, and you said we have to be a conditional no except, and you also said, well, the future new code would either be annotated with a no except or the throws attribute. Would that mean that the library also needs a conditional throws?
So the conditional no except is a conditional throws in that world. So if we are in a world where we're teaching people for new code, write exactly one of no except or throws, there's still room for conditional no except to compute it if you can compute it. As a simple example, if you're using a vector instantiated with an allocator you know doesn't throw, then your conditional no except will become no except true. Otherwise, no except false would be equivalent to throws. That's the idea.
Okay, so the annotation throws it's just a teaching tool, but not so much. If you don't put no except on it, then it's...
Yeah, I see what you mean. So certainly in a world where we didn't have the existing dynamic exceptions at all, what I just said would be true. But you are correct that in the conditional case, you want to say where if it is true, which one is it? So yes, you're correct. You would need in that world a conditional throws as well. I think I have that in the paper. I like to live in the future and fast forward to the world where it's just one or the other, but you are correct.
Quick second question, maybe?
Can we do one at a time? Sorry, thank you very much for your question, but we only have time for one or two more, please.
You said there were some code bases that banned exceptions, and there were even more where you were not allowed to use RTTI. But that confused me because I thought exceptions relied on RTTI.
So if you look at, first of all, if you look at the numbers, if I said it backwards, I apologize. The actual data on the slide showed that it was like 2/3 of projects enabled RTTI, whereas it was only about half of exceptions. So there is more RTTI use in the wild. There is less banning of RTTI than of exceptions. However, yes, you are correct that exception handling does require RTTI. So that order is natural. The thing that, however, is the compiler can generate a dependency where you must have RTTI to enable exception handling, and that's common. Theoretically, a compiler could also just implement exception handling with just enough RTTI to do the void star to base cast, to base star cast. Yes. I'm going to cheat one more, but then we have to go. Sorry, John.
Thank you for your talk and for the work. So one thing that came to my mind is, are you worried about that these two words of information that you can convey using std error, like most of the languages that use, modern languages that use error codes usually have some kind of type where you can put in anything. And are you worried about that if they propagate, it would be hard for the programmer to always choose different codes and be sure to handle the right error?
So it's a good question that will have a long answer. The short answer, take a look at that section of the paper and also the related papers like Niall Douglas's in particular that talk about the error code. The short answer is the error code is two words because one of them is like the payload, usually an integer, but it could also be a pointer to a dynamic exception if you're wrapping one of those. And the other one is a category, which is usually a void star to a singleton, to the category of error. That can represent any conceivable error in POSIX, in Windows, in Corba, in COM, in all of those things, and allow customization. So including, as I mentioned, it can wrap a dynamic exception, which is how we can go from if we call a function that throws a dynamic exception, and we're a throws function, a new style value throwing function, we can wrap the dynamic exception in a std error and then propagate it with bitblit. So that's the short answer, but please see the paper for the answer.
Thank you.
Thank you again, and I hope you enjoy the rest of what John has to say. Thank you, John.